Okay, so this revision video is for your differentiation assessment, and what I'm going to do is I'm going to look at the summer 2019 question 3 exam question. Your differentiation assessment will be the 2020 question that had already been drafted. Now in this chapter, which is chapter 3 in your manual, there are 5 different sections, and the question will be made up of 3 of them. There's a summary at the end of chapter 3, which kind of describes the different, it's the very, very basics that you need to know. Usually the problem people have with this question is they mix up sections, so they try and do they mix up partial, parametric and implicit differentiation. Now this, as an exam question, it doesn't have all 5 different things, just has 3, and there's different ways that they can go as well. So we'll start off anyway with question 3a. So we have, we've got y of x is the cube root of x. So there's two different, it says implicit differentiation, so it is about implicit differentiation. There's 2 ways the implicit differentiation can go. One is like this question where you've got some function, so examples would be cube root of x, square root of x, log of x, even e to the x, inverse sine, inverse tan. And to find the derivatives of these, you can use implicit differentiation. Now the question will guide you through. That's the first type. The other type is if you're given a curve, which is an equation, a relation between x and y, and every solution of the equation is plotted, you get a curve, and there might be a question about find dy dx, etc. Okay, this one is the former type. So part 1 says use implicit differentiation to find dy dx if y cubed is equal to x. Now, ultimately that's giving you implicit curve, so the questions are more or less the same thing. What I would say at this stage, I'm just looking, there's a funny flashy light going on here. I recommend in all cases that you write the y as y of x. So what we're dealing with here is y of x cubed equal to x. And what we want to do is we want to differentiate both sides of this with respect to x, and the language is implicitly, we know that y is supposed to be a function of x. The reason that I write the y of x is so you show this understanding, but also that you see that there's a chain rule here, because you've got an inside function y of x and an outside function x cubed. Using the chain rule says differentiate the outside function. The outside function here is x cubed. The chain rule says differentiate the outside function, 3x squared. The chain rule says evaluate at the inside. The inside here is y. And then the chain rule says multiply by the derivative of what's inside. And the derivative of y of x, well, all you can say about that is that it's dy dx. Equal to the derivative of x, which is equal to 1. Now it's asking us to find dy dx, so all we have to do is divide both sides by 3y squared, and so we find that dy dx is equal to 1 over 3y squared. And that is part 1 done. In the other type of question, it'll be this relation will be far more complicated. You might need product rules and everything, and then you'll have an equation here with x's, y's and dy dx's, and it'll be your job to solve that for dy dx in terms of x and y. This one is particularly easy, but of course this has more parts to go. Part 2, use the fact that y squared is x to the power of 2 over 3, so this y squared is x power 2 over 3, to write dy dx in terms of x alone. So this is pretty straightforward. It said y squared is equal to x to the power of 2 over 3, so 1 over 3 times x to the power of 2 over 3. Basically that's all that it said. Part 3 then says note that y of x, the original function, the y of x, the original function was the cube root of x. Use the power rule of differentiation to find dy dx directly. So this is saying, okay, differentiate x to the power of 1/3 using the power rule. Now the important thing is here is that where does the power rule come from? It actually comes from an argument like this. You need implicit differentiation to prove the power rule. So what does the power rule say? It says multiply by the power and reduce the power by 1. So 1/3 minus 1 is minus 2/3. And you can leave that like that. And then the question at the end is, do the two answers agree? Are these two things equal? Now they look a little bit different, but they're not, because a negative power is dividing. So this is 1/3, and x to the power of minus 2/3 means divided by x to the power of 2/3. So are they equal? Yes, they are. So that's that question done. 6, 7, 8 marks, how bad? Okay. We'll move on to question B. So the second question is about the teeth of a gear being a part of a particular curve called the involute of a circle. And there's an example of the curve with a picture. This is on page 225 of your manual, you can have a look. And it says find dy dx in terms of t. So what I'm going to do is I'm going to write down, it's a parametric curve, so x and y is given in terms of a parameter t. So we'll write these down. X is equal to cos t plus t times sine t. So that's the x coordinate in terms of t. And the y coordinate in terms of t is sine of t minus t times cos of t. Actually, there's one thing I want to do. I just want to go back on this. So the important thing in a maths question in terms of like exam technique, and you will have time for this in your assessments, is you say to yourself, have I answered the question I was asked, and does my answer make sense? So looking at one, use implicit differentiation. I did. To find dy dx, I did it. I answered the question I was asked. This answer seems to make sense. Second thing, use this fact to write dy dx in terms of x alone. Have I written dy dx in terms of x alone? I have, and the answer somehow makes sense. Use the power rule of differentiation to find dy dx. I did this. Do your answers agree? You must give a yes or no answer. I gave a yes answer. So that's how you do it. Did I answer the question I was asked? Does my answer make sense? Okay. And you should have time to do that for all these questions. Okay. So the question here is looking for dy dx in terms of t. Now I mentioned that summary at the end of chapter 3. One of the things you need to know is if you have a parametric curve, that dy dx is equal to dy dt divided by dx dt. Okay. So we need to differentiate the y divided by differentiate the x, and this is what we're asked to do. Now we'll be a little bit careful. We'll do it all in one line just for a bit of space reasons. Okay, let's differentiate this. Now you want to be a little bit careful here with signs and stuff. Now it's a sum, so you can differentiate term by term. So the derivative of sine of t, there will also be a tables that you can download. The derivative of sine of t is cos of t. But differentiating this, you have to be a little bit careful with the sign, the minus. What I recommend is fix the minus and then go off and differentiate t cos t. Now it's t multiplied by cos t, which means when you're differentiating this you must do a little product rule. And you can look in your tables for the formula for the product rule, and it says it's the first thing by the derivative of the second thing. The derivative of cos of t is minus sine of t, plus the second thing, which is cos of t, by the derivative of the first thing, and the derivative of t respect t is 1. So it's a product rule, and also I'm just being careful with the sign. So you can say fix the minus, and then go off and differentiate, fix the minus here like this. Divided by dx dt, differentiate again, differentiate term by term, the derivative of cos t is minus sine of t. Okay. And then again, this is also a u and a v for a product rule for the derivative of this. So it's and the plus makes it a bit easier. So it's the first thing by the derivative of the second thing. The derivative of sine of t is cos of t. plus the second thing, which is sine of t, times the derivative of the first thing, which is 1. And now I'm not too big on simplifying things, it's usually not necessary, but I think there's very easy simplifications here. You have cos t minus cos t is gone, and you minus minus is plus, so you get t sine t. And then on the bottom we have sine t minus sine t, which is gone, and you've got t cos t. Now there's more simplifications you can do with that. In fact, that's equal to tan of t, because t divided by t is 1, and sine t divided by cos t is tan t, but I'm quite happy with that as an answer. Okay, that's dy dx in terms of t, and the second thing is find the equation of the tangent to the curve at t equal to pi. Okay, so as soon as you see equation of the tangent, you've got to be thinking that tangent, it's a line, and you've got to be thinking y minus y1 is equal to m times x minus x1. Okay, now have a little bit of a think here. So the answer is going to be some equation in x and y, but the question is, so the x and y are just going to sit here, what's the slope and what's the point? Now at this stage you have to know that the slope of the tangent is dy dx, and we're interested in the slope of the tangent at, it says it here, at the point where t is equal to pi. So all we have to do is substitute pi into this, and so without simplifying you get pi sine of pi over pi cos of pi. And you can do whatever, bang that into the calculator. It's very important that you are in radians. If you aren't in radians, it's not true, for example, that the derivative of sine is cos, so you have to be in radians, and if you're in radians you'll find that this is equal to 0. Okay, so we know that the slope of the tangent is 0 at least, and then the other thing is, oh well, how do I get the point? And this is where you have to understand that what a parametric curve is. At each, there's a parameter, and each value of the parameter gives you a point on the curve. And how do you find that point in the curve? You substitute the parameter in to these I think are called parametric equations. So if we want to find x1, what I have to do is substitute pi into this. So you get cos of pi plus pi times sine of pi. And that I am reasonably confident. I have to be a bit careful here now. And this is equal to, well, this is equal to 0, and this is equal to minus 1. And then y1 is equal to sine of pi, which is 0, plus, minus, I'm substituting this, minus pi times cos of pi. And if I'm careful, this is minus 1, this is minus pi by minus 1 is pi. The calculator will do this for us. Okay, I think that's okay. Now it might be possible to look at the graph and make sense of the answer at the end. Okay, so y minus y1 is equal to m times x minus x1, which is minus 1. But 0 times anything is itself, and adds a pi to both sides, y is equal to pi. It's equal to a constant. Now if you have a little look at the curve, so this is the question is answered, right? But just if you're trying to say, does this answer make sense? The curve does something like this, and at x equal to 0, the curve is kind of coming down, but at the top here, if you look at it, the coordinates of this, it's around x equal to minus 1, and the y coordinate is a bit bigger than 3 pi, and the slope is 0. So it's like 0x, and it cuts of course at pi as well. So if you just look, it's in the smallest thing, look at the picture and see that that does make sense. Okay, let's go through those things. Have I answered the question I was asked? Here in part B, I was asked, or in part B1, I was asked, find dy dx in terms of t. I have done that. Dy dx is equal to this. Good. Find the equation of the tangent to the curve. So have I gotten, here is the equation of the tangent. Done. Sometimes there it might say, find the slope of the tangent, in which case you're finished there. Now you might have done this extra, and then you might go back to, Now I'm not going to punish you for doing more, but you might come back and kind of like scribble that out and say, oh well, actually this is all that was enough for it. Do the answers make sense? It's probably difficult to say that this makes sense or not. This shows that this second one, the answer does make sense. Okay. Now, part C. Now, in terms of hints, what's coming up, I don't want to be too prescriptive because there are genuinely 5 different things and 3 of them will come up. But usually, I do ask this question. I like this question. That's not a guarantee. To be honest, you should just prepare all of them, to be honest with you. Okay, so what have we got here? The angular frequency in radians per second of a harmonic oscillator. So you got some kind of an oscillator, a spring, something like this, of a certain mass and spring constant is given. There's a formula. Now, the formula is square root of k over m, and that's important, but really the hint is given here. So it's saying that omega, the angular frequency, is k to the half m to the minus half. Now, the reason I've done that is just in case people didn't have the algebra. Differentiating the square root of k over m is possibly a little bit difficult. Differentiating this is going to be quite easy. Okay. Use differentials to approximate the error. Oh, okay. We're going to be using this formula to calculate the angular frequency, and we've got measurements of the spring constant, 20, with an error of 4, maximum error. And mass is measured to be 100 grams, 0.1 kgs, with an error of 0.005. So we've got measurements for K and M, we're banging it into this formula, and we're saying, oh, this is the angular frequency, but there's measurement errors, and how much uncertainty in what the values of K and M are translating to how much uncertainty in our calculation. So the easiest thing to do, first of all, is just do the calculation, omega 0. K is 20. Power of a half times mass, which is 0.1 to the power of minus a half. Now, we don't know yet how many significant figures to take here. To be very, very safe, we can take 5. We'll be reducing this a little bit later on. So we're getting 14.142. And we can worry about units later on, although everything's in SI units, so it will be radians per second. Okay, now there's uncertainty in this, and there's uncertainty in this. We use differentials. So the thing at the back, okay, so the way this works is, okay, there's an error in the calculation of omega, which is approximated by the maximum of the differential. And this yoke is, you do rate of change of omega with respect to the first variable times the error, plus rate of change of omega with respect to the second variable times the error. This is all in the manual. And you use absolute values to make a worst case scenario, to make this a max. So it's going to be differentiate partially omega with respect to k times error in k, plus differentiate partially omega with respect to m times the error in m. And this is, once you're here, you've done all in a way to remember. This is the difficult part. Okay, so what have we got? Differentiate this with respect to k partially. Now remember, everything else that isn't k is kept constant. In particular, m to the minus a half here is kept constant. And now I just differentiate k to the half with respect to k. And it's just the power rule, so it'll be half multiplied by the power, reduce the power by 1. The absolute value doesn't come into play here because all these things are positive. Power of minus half doesn't look positive, but it's just division by k to the half. It is positive. Times delta k. We will need the absolute value here, as we'll see in a second. So absolute value. Differentiate this now with respect to mass. Now the partial derivative means everything that isn't mass is kept constant. So k to the half is a constant. So if you're differentiating this, fix the constant k to the half. And then the derivative of m to the minus a half is multiplied by the power minus a half, reduce the power by 1, so it'll be minus a half minus 1, which is minus 3 over 2. Absolute value, and then the error in the mass. Now what we have to do is evaluate these derivatives at the measurements, and these are the errors. So we get the mass is 0.1 power minus a half, times 1/2. K is 20 to the power of minus a half times the error in K is in the question is 4 plus, now this thing is negative, so the absolute value makes it positive, just forget about that minus. Take a K to the half, which is 20 to the half, times a half, times M, which is 0.1, to the power of minus 3 over 2, times the error in the mass is in the question is quite small, 0.005. Bang all this into the calculator. So we get 0.1 to the power of minus a half by 1/2 by 20 to the power of minus a half by 4 plus 20 to the power of a half by a half by 0.1 to the power of minus 3 over 2 by 0.0, it's a bit of a nightmare in the calculator, 0.005. It comes out as 1 point, I'm just going to take four significant figures, 1768. Now what we do now is, this approximation is very, very rough.